The usual things are given, like frictionless pulleys, light pulleys, etc. This is a 5 kg block. This is a 2 kg block. The question is, what is the acceleration of the 5 kg block? Obviously, 5 kg block should go downwards, and then because of tension, this fellow should go rightwards. There are 2 strings involved, so we need to take 2 tensions. But before we write equations, how about finding out the relationship between the 2 accelerations? Because movable pulley is involved. So let's think like this. This point reaches here. This is x distance. Then this x plus this x, 2x will be released, and that 2x will be pulled by this 2 kg block. Now in reality, that's not going to be the case really. That 2 kg block will go to the left, but that's no problem. This way of thinking is only to find the relationship between the 2 accelerations. In reality, it must go to the right side and this must go downwards. So 2a and a. Once that is known, we can just start writing the equations. For 5 kg block, net force must be downwards because acceleration is downwards. Net force downwards is 5g minus t. This movable pulley is light, so no force acts on it net. Then this block as a system, net force must be towards right. T dash is the only force. Mass times acceleration. Can you solve for A? and see if you are getting A equal to 5 by 13 G. Any questions? Let me know. No questions, so I suppose I can move on. Let's now talk about friction. When a block is kept on a surface, then there is electromagnetic interaction. And this electromagnetic force can be shown in this way. As a general case, earlier we have ignored friction, so we have been talking about normal reaction, just vertical. But that's only a special case. General case is what you are seeing in front of you. It can make some angle, it can be inclined, this electromagnetic force. So it is going to be equal and opposite, just like any other force following Newton's third law. So what is shown is the force on the surface, on the block by the surface. This is the force on the block by the surface. So block will apply an equal and opposite force on the surface. So the surface will experience force which is opposite in direction, like that. That's what surface will experience. So that's the story of contact force. We have been talking about normal reaction, ignoring friction completely. This contact force can be broken into two components. One is the vertical component, other one is the horizontal component. Vertical component is what is called as normal reaction. And if friction is zero, then contact force itself will be vertical. If friction is zero, contact force will not be inclined, but it will be vertical. But generally speaking, the normal component, the perpendicular component of contact force is called the normal reaction. And the other component, which is along the plane, that component is called friction. Right? So the electromagnetic interaction between the two surfaces gives rise to a contact force, which is what is shown. Note that it must be acting from the surface, but vectors can be moved. So it is shown to act, it is shown somewhere else, but it will act from the surface. And this contact force has got two components. One is the normal reaction, vertical, and the other one is the frictional force. So that's about the origin of frictional force. It is always along the plane. Along the plane. This is the plane. So it will be on the plane. Friction force will lie on the plane. Normal force will never lie on the plane. It will be perpendicular to the plane. Frictional force is experienced under different conditions. A very common condition is that of sliding motion. Sliding, rubbing, that motion. When that motion takes place, then this type of friction is called kinetic friction. For kinetic friction, sliding is absolutely necessary. Sliding. Friction can be present without sliding also, but that is not called kinetic friction. Kinetic friction means sliding or rubbing. When a wheel rotates at its own place, like somebody just rotating the wheel round and round and round, and it rubs as it rotates the ground, then that is rubbing. But when wheel moves in a bicycle, not just rotating in its own place, but moving forward, then it is not supposed to be rubbing under ideal conditions. Bicycle or any wheel for that matter is not meant in this way that it should rub with the ground. It is not supposed to rub with the ground. When you are riding bicycle and due to certain emergency you have to apply brakes, then sometimes you will see that there will be rubbing, and you may lose control also when there is rubbing. Otherwise you don't lose control easily if you know how to ride. So losing control, that's an indicator that your bicycle is sliding, not rolling. Bicycle is supposed to be performing rolling motion. Rolling has no rubbing, ideally speaking. So whenever we think of rubbing, we think of kinetic friction. Otherwise, friction may be present, but it would not be called kinetic friction. Now the question is, what will be the direction of kinetic friction? What kinetic friction tries to do is to oppose the relative motion. It doesn't like relative motion. This is what kinetic friction tries to do. It tries to oppose the relative motion. So if I slide a block on the ground, then kinetic friction would not like this block to slide on the ground. It would like it to stop sliding, stop relative motion. It just wants to stop the relative motion. It just wants to stop the relative motion. It doesn't mind if two fellows travel with the same velocity. It's the relative motion which is a problem. The two fellows can move together, that's no problem. But when there's a relative thing, rubbing, taking place, then it's a problem. Otherwise, two things are connected to each other tightly and they're both traveling at a high speed. Where is the kinetic friction present between them? Zero. If you tight two things and then both of the things move quickly, kinetic friction is zero. Between them, kinetic friction is zero. So it's the relative motion, and that obviously means that direction will be so as to oppose the relative motion. So suppose we have got one thing, let's say a block sliding over the floor. One block sliding over the floor. Block is going to the right side. Floor is not going anywhere. So kinetic friction would like that either floor should also move with it, which is not going to be working. So it would like it to stop. So that means it will act in the opposite direction. Opposite direction of the motion. Block is going to the right side. This kinetic friction will act on the left side. Okay? So that's how you decide the direction of kinetic friction. Now comes magnitude. Magnitude is given by, or let me put it this way. Contact force has got two components. The vertical component, that's very interesting point by the way. The vertical component, friction is not the vertical component, friction is the horizontal component. The vertical component decides the magnitude. That is something which is very interesting about friction. It is horizontal force, but the vertical component of contact force decides its magnitude. So talking about kinetic friction. Kinetic friction is proportional to the vertical component, which is called a normal reaction. So frictional force, kinetic, is proportional to N. And this proportionality sign is removed by introducing a constant that is often represented by mu symbol. Technically, let's call it mu k, k for kinetic. Mu is a constant but not universal. Mu depends on the two surfaces that are involved. Is iron rubbing the wooden surface, or iron is rubbing the glass surface? Both surfaces that are involved, mu will depend on that. It's not a universal constant. Another thing is that it has got no unit of its own. You can see that frictional force is a force, and normal reaction N is also a force. So if both sides are forces, then force upon force is just going to be dimensionless, unitless. So mu has got no unit of its own. It's often decimal, but that's not necessary that it will be decimal. It can be more than one also. It just depends which are the two surfaces that are in contact with each other, so in which relative rubbing is taking place. Now this point that its magnitude is decided by vertical component, that gives rise to some interesting situations in real life situation. Generally we say in physics that a motion can be broken down into motions in X, Y, and Z direction. And we deal with X direction separately from Y direction. and y direction separately from z direction. We do this quite a lot in physics. And it is often independent type of analysis, x direction independent from y direction, from z direction. But here you have got a situation where a horizontal force is decided by vertical force. So that's something which is very interesting about friction. When we have talked about static friction, then you will realize this, I think, on your own, that how perpendicular force is deciding the horizontal force's magnitude. Something as simple as putting a book here on the wall, it will obviously fall. You can't put a book on the wall, it will fall, right? But if you just push the book with your hands, the book won't fall. Now, fall of the book is vertical motion, and what you are doing, you are pressing the book, which is a horizontal force. So due to your horizontal force, book is not falling, which has to do with the vertical force. So such interesting things can be understood due to this. But that example that I was giving you falls under static friction, and that will come later. We have done so many problems without taking into account the horizontal component of the contact force. Basically, the problems that we did, surfaces were smooth, so there was no component in the horizontal direction of the contact force. There was none. Contact force was purely normal reaction. So now we can very easily incorporate frictional force in any types of problems that we have done. You just have to look for one more force. Say, for example, a situation like this. There is a block kept on the table. It is pulled towards the right side by F force. Its mass is given to you. There is friction present, and the coefficient of kinetic friction is given as mu k. Then what is the acceleration? What is the acceleration it is going to have? You will analyze two directions, and if we are interested in x direction only, then earlier there was no need to get into the y direction, but here the normal reaction which is in y direction, that is deciding the magnitude of frictional force. Normal reaction is deciding the magnitude of frictional force. So we will have to get into the y direction also. For x direction, F is on the right side, block will accelerate on the right side. Frictional force, kinetic, does not like relative motion. Surface is not going anywhere. Block is going to the right, it doesn't like it. So frictional force acts on the left side on the block. And by the way, frictional force will also act on the ground, on the surface that is, and frictional force would want the surface to accelerate to the right side. Surface will of course refuse to do that, but this Fk will act on the surface towards the right side. So Fk is acting on the surface towards the right. Anyway, surface is not going to be our system. block is going to be our system. Yes, any questions? Go ahead.
So, if we have this frictional force also acting towards the right side and the force also acting towards the right side, so in that case, a frictional force, this so-called force won't act as an opposing force. So, how do you call that?
Where is friction force acting towards the right side?
Sir, right now you mentioned that is my question.
I mentioned in which context? Surface context. On the surface, Newton's third law says that forces are always equal and opposite. So on the block, if frictional force is acting on the left side, on the surface, where will it react?
Yes, sir, towards the right side.
Towards the right side. But that is acting on the surface. And this F is acting on the block. So this F and that F have got nothing to do with each other. But this F and this F have got a lot to do with each other. So on this system, net force on the right will be this F minus this F. That's it. And that net force will be mass times acceleration. But we know that Fk is given by mu k times n. This is n. Fk is given by mu k times n. Now the problem is, how do we know n? That's where vertical equation is important. So vertical equation also you need to write. So what is the vertical equation? Can anybody tell me what is the vertical equation before I write it on the board?
So mg will be equal to n equal to the normal reaction.
Yes, mg is equal to n. Because there is vertical equilibrium, block is not going up or down, so mg is equal to n. That's it. So what is acceleration? Well, you know the answer now. F minus mu mg whole divided by small m. That is the answer. Any questions? Let me know. Okay, then I can move on. Let me now illustrate how to handle inclined plane in case of friction being present. You have already handled it without friction. Now we need just one more force. So let's say this block is here. This is the inclined plane. Mg is shown, normal reaction is shown. it will obviously, if it is accelerating, it will accelerate downwards. It's not going to go up. Let's say it is accelerating downwards. The motion is downwards. Friction doesn't like it. Friction wants inclined plane, and kinetic friction likes inclined plane and the block to be in no relative motion. But it is in motion, so frictional force kinetic on the block will be in opposite direction. On the block, it will be in this direction. Frictional force will also act on this inclined plane. Can you show me what will be the direction of this frictional force on this block? You can use the pointer if you want on the board. I'm repeating the question. What will be the direction of kinetic friction on the inclined plane? This one, which is not shown in this figure. You are taking it right, left, both. Is it right or left?
So it would be towards the left on this inclined plane.
Towards the left on the inclined plane. Like that. Yes, this finger. This way. So if at all you have to take this triangle as your system, in some problems you do have to do that. Then you will take Fk like this, left. Okay, now Fk is shown. We are ready to write equations. Two equations, one along the incline, one perpendicular to incline. Along the incline. Acceleration is in this direction. So net force in this direction will be mg sine theta minus Sk. That's it. That will be equal to mass times acceleration. Now, Fk is given by nu times normal reaction. This is normal reaction. So we need normal reaction. So writing this equation, vertical sort of thing. In this direction there is no motion. So n should be balanced by mg cos theta. N equal to mg cos theta. So kinetic friction will be mu times n, which is mg cos theta, mu mg cos theta. The job is almost done. Copying this, Fk, copying this, mu k mg cos theta. That will be ma. Cancelling m everywhere. This is the final result. Any questions? Let me know. Analyzing contact force is no problem once you know its components. Components of contact force are normal reaction and friction. Frictional force is given directly, 3 newtons. If you know the normal reaction, magnitude of contact force is going to be no problem to tell. the body is sliding, vertical equilibrium is going to be there. And that means normal reaction should be equal to mg. M is 400 grams. Taking G as 10, mg is 4 Newton. So 4 Newton must be N also. Normal reaction is 4 Newton. Frictional force is 3 Newton. Magnitude of the resultant, where the components are making 90 degrees with each other, can be easily obtained by this. Because angle is 90, it is so easy. Just root, like Pythagoras theorem. So root of 3 square plus 4 square, 5 Newton will be the contact force. Regarding the direction, angle made by contact force with the vertical. If the body is sliding towards the right side, frictional force would not like it. It will act in opposite direction so as to stop the body eventually. The frictional force is acting leftwards. Contact force is the resultant of normal reaction and friction, which will be in some direction like this. We want the direction, we want the angle with the vertical. This is what we want. So tan theta will be this perpendicular, which is F upon N. Tan theta will be this F upon N. Small f. Small f is 3 and capital N is 4. 3 by 4. 3 by 4. If tan theta is 3 by 4, how much is theta?
Sir, 37 degrees.
37 degrees. 37 degrees. Any question, let me know. And by the way, this angle, which is between contact force and normal reaction, is called angle of friction. This is called angle of friction. Let's now do this problem. This is 1 kg block. This is also 1 kg block. Between this surface and this mu is 0.2. Between this surface and this mu is 0.2. This is 0.5 kg. Pulley, string, the usual situation, usual things apply. Frictionless, massless, those types of things. First question is, what is the acceleration of, well, everybody will have the same magnitude. What is the acceleration? What is the tension? Both, here also, here also. There are two strings used. Acceleration and tension. Acceleration is going to be same in magnitude for everybody. Let's say this is T, this is T dash, and A is downwards for this, rightwards for this, rightwards for this. For this system, gravitational downwards 0.5 G, electromagnetic tension upwards minus T, net downward force is 0.5 G minus T, and that will be equal to mass times acceleration. That's one equation. We are having three unknowns, A, T, and T dash. So we should be needing three equations. Then let's take our system as maybe this. On this, frictional force is acting on the left side, gravitational downwards, normal reaction N2 upwards, acceleration is rightwards. So T dash minus this friction. This friction will be how much? Mu times N2. So T dash minus mu times N2 equal to mass, which is 1, into acceleration A. Then for this system, acceleration is towards the right, T is to the right, this T dash is to the left, then this friction is mu N1, which is to the left. Net force is 1 times acceleration. How do we find N1 and N2? There is vertical equilibrium here. There is vertical equilibrium here. So N1 will be mg, 1 into g. N2 will be mg, 1 into g. N1, N2, both of them are going to be 1 into g. This is known, that is known. It should be possible to find A, T, and T dash. Please find out and verify if you are getting answers as these. Any questions? Let me know. Here mu is 0.2. Masses are given. All the usual things about pulleys and strings are given. You have to find the two tensions, left and right. That's your assignment. We stop now.